I'll finish this lecture on global optimization of non-convex mixed integer nonlinear programming by talking a little bit about bound tightening. And these are techniques that ensure that we can get tighter bounds on the intervals, which then in turn give tighter outer approximations. And so the goal is to simply try to reduce the range of the bounds that we have on some of our variables. Because tighter bounds give us tighter relaxations, right? I can easily draw a simple example. If this is a nonlinear function, if my bounds are, if these are my bounds, then the best I can do is something like this in white. If I have if I have tighter bounds, if my bounds are over here, then I can do something like this. And if I have really, really tiny bounds, then I get a very, very tight approximation. So that's why we want to make these bounds as tight as possible. And there's two techniques. One is feasibility-based bound tightening, and the other one is optimality-based bound tightening. So conceptually, what I'm trying to do is I'm trying to, over the feasible set, I want to push the lower bound up as far as I can. So that's minimizing the value that I can take inside the feasible set. So I try to find a value that allows that still valid, and I also try to push the upper bound down as far as possible. So first, this is feasibility-based bound tightening. It's known in the constrained programming community, and it's done for nonlinear optimization and mixed integer linear optimization solvers. And these are very simple rules. So we're just going to look at, given bounds on one of the variables, how do I get bounds on another variable? So here's one example. I have xj is xi cubed, and I assume that I have bounds on xi and on xj. And I now can tighten the interval on xj by observing that it will, because xj is xi cubed, it will only take values in that are intersected with the interval of the bounds that I put into the function. So the lower bound that xi cubed can take is li cubed, and the upper bound it can take is ui cubed. Those are lower and upper bounds on the value of the cube. And I can, at the same time, I can go the other way around. So I can also start at xj. If I've now tightened bound on xj, and I can maybe get a tighter bound on xi by observing that I can invert this operation. So I can go from xj to xi by taking a cubic root and just safeguarding it in the right way. Okay, so here's a little exercise. Given our old friend, the bilinear function, with the following bounds. So z is x times y, and my bounds are 1, 1, 0 are the lower bounds for x, y, and z, and the upper bounds are 5, 5, and 2. And your task is to tell me if you can tighten any of these bounds. Okay, so I'll give you a quick couple of minutes, and then somebody can press a buzzer or something, and we can do a little game show, and you can tell me what the answer is. So the trick is, what I did up here is I used this nonlinear expression. I had a bound on xi, and then I know that I can get a bound on xi cubed by just cubing that bound. So I'm going to do this. I want to do the same thing here. So can somebody give me a tighter bound on a lower bound on z? So somebody, 1, excellent. So I can, because z is equal to x times y, which is greater or equal to, the lower bound on x is 1, the upper bound on x is 1, so that's greater or equal to 1. So I can replace this and put a 1 here. What else can I do? I think there's one more I can do. The lower bound on, decrease the lower bound on x or the upper bound on x? We don't want to decrease the lower bound. That makes it worse. So we want to decrease the upper bound on x. Okay, how are we going to do that? Somebody? X, I can write x as z divided by y, right? And I'm allowed to do that because y is non-negative. But if I didn't know that, I would safeguard that. So y non-zero. And then I want to look for an upper bound. So that is less than or equal to. An upper bound on z is 2. And I take a lower bound on y, which is 1. So this is 2. So I replace this guy here by a 2. And I can do the same for this guy here. And as an exercise, if you want to, you can just write down a problem where you minimize z subject to this constraint and construct the McCormick underestimator. So you know how to do that, both for the original and then for the new bounds. And you will see a marked difference in the value of z. So the lower bound that you construct will be much higher than the previous lower bound. A little bit. It will be 1. So, okay, not so impressive. But if you wanted to, you can put a different objective function there and you get more impressive results. Okay, cool. So this generalizes to other functions, right? We can do this for other functions, and one example are linear expressions. So when I have an affine or linear inequality constraint, for example, such as this one here, where I have xk, a linear equation with a constant term, and then some aj's, I divide my summation, my sum, up into the positive coefficients, where the aj's are positive, and the negative ones. And then I can construct, a lower and an upper bound. So if I take all on the left here, I take a0, and I construct a value that's a lower bound. So for the negative coefficients, I want to make this term as small as possible. I'm going to put in the upper bounds that I have on my variables, so that drives it down as far as possible. And when the aj's are positive, I'm going to put in the lower bounds that I have here. So this is a valid lower bound on the right-hand side here, and hence on xk. And then I can do the same on the right-hand side. So I look at the negative coefficients. I want to make those as large as possible. These terms here, the blue terms. And to make those terms as large as possible, I put in a smaller possible number because I have negative coefficients. And when I have positive coefficients, then I put the upper bound of uj there. Okay. And then once I constructed these bounds, so now the left-hand side here is now my bound lk. That's now a new bound on my variable xk. And uk is a new bound on my variable xk, the upper bound here on the right. Then I can pick any of the other xj's that I have in my expression and repeat. So now what I do is I just pick an xj and I rewrite it xj in terms of I solve this equation for xj basically, and then I again play the same trick where I have the lower and the upper bounds in there. So I can now repeat this for all the variables. And so what I would do is I first do this for the resulting variable. I get a bound for all the resulting variables, and then I can go back and see if I can tighten any of the bounds on all the other variables that I had. And you can maybe get better bounds from convex combinations of inequalities. In particular, if you can eliminate variables, then you will have fewer expressions here. So if you can add two inequalities, you might be able to get tighter bounds there. And you can still do this. In general, we can push these bounds up and down the computational graph. So here's again our sample optimization problem that we've been solving, and its corresponding computational graph on the right-hand side here. And so one thing I can do is I can always get bounds on the new variables by just pushing my variables x1 and x2 through these or the bounds that I have on the variables x1 and x2 through these expressions. So as long as I do this correctly, I need to know that if I square a variable, then I have to square the bounds. So as long as I do this correctly, I can get correct bounds, for example, on x9. But I can also go back. So I can also I can push bounds up to x4, for example, and then by using the inverse operation, push these bounds back down the computational graph. So here, for example, I get a bound on I propagate a bound to x8, and then I can potentially tighten back down to x2. So once I have a bound on x8 from x9, I can then push this bound back down using the square root operation to this value here. And there's lots of tightening you can do, and typically we would do this bound tightening until it no longer gives a large improvement. So you would monitor by how much you're reducing these intervals, and when there's a trailing off, then you would stop doing this. So this is very fast and efficient to implement because you're just walking through the computational graph. You're just applying these operations inside the computational graph. But it can be slow to converge, and there's examples where it doesn't terminate in a finite number of steps. So it's an infinite process, and it can be slow. And in particular, you will see a lot of improvement early on, and then this improvement will tail off. And then that's where you want to stop doing it because there's not a lot of gain for a lot more effort. So there's other techniques which we want, and one of those other techniques is optimality-based bound tightening. So this is a more it requires more effort, but it also gives you potentially tighter bounds. So we know that just minimizing or maximizing the range of a variable over the non-convex feasible set is really hard to do. So let me draw a picture of what I mean by that. So let's say we have two variables, x1 and x2. And we have a non-convex feasible set. That's this set here, this red set. And I have maybe initial bounds on x1 and x2 that are, it's just between 0 and some upper value here. I need to make this a bit longer. But these bounds are not tight. So my initial bounds might be this box here, for example. And so you can see that this box is quite loose. And ideally what you would want to do is you would want to say, okay, I want to find the sort of lower bound on x1 would be something that would be, the ideal value would be here, and the upper bound on x1 would be here. And so to find this value, what I can do is I can maximize, I can minimize, or maximize, in this case, x1, subject to x lying in my non-convex feasible set. Right, this little bean that I've drawn there. But that's a non-convex, nonlinear optimization problem. So that's a hard problem to solve. So instead, what this technique does is it creates, it starts off with some polyhedral, for example, approximation of your non-convex set. And I'm just drawing something here that I have no idea how to construct. And maybe there's a one there. And so I would, instead of minimizing over the red set, I can now minimize over the yellow set. And then the bounds that I would get would not be as tight. So this would be the upper bound that I would get if I maximize over this set. That's as far as I can take it. If I minimize over the set, I would maybe get something over here. And I can repeat the same operation in the other axis. Now there I wouldn't see an improvement. So what I have is I basically use the same polyhedral approximation that I've constructed from the computational graph previously for my nonlinear expressions. I can use that, and I can just minimize the range and maximize the range of the variable. So minimize the variable and maximize the variable. By minimizing the variable, I will get a lower bound. By maximizing this variable, I will get an upper bound. Right? If I maximize the variable, I try to go as far as possible to the right of the polyhedral set. I can go up to here, and I can potentially tighten this bound. So now, when you tighten bounds, you can also, again, tighten this relaxation. But that's, maybe you don't want to do that here. Note that you still need to solve 2 linear optimization problems per variable on which you need to tighten these bounds. So that's actually quite expensive. So there's these 2 ways of getting tighter bounds for global mixed integer nonlinear optimization. One is the feasibility-based bound tightening, where we walk up and down the computational graph, pushing bounds up to the root nodes or pushing them down, back down to the leaf nodes by using the operations inside the computational graph that I have here. And this is a way that is relatively weak, the bounds that you get, but it's fast, it's cheap to do, computationally very efficient. The optimality-based bound tightening, on the other hand, is expensive because you need to solve 2 linear optimization problems per variable. So in this case, I have 2 variables. I would need to solve 4 linear optimization problems. That's much more expensive than the easier tricks that I showed you. But it gives you potentially stronger bounds that you might not get otherwise here. And the way to do this optimality-based bound tightening is to do it over a polyhedral relaxation, because then these problems are linear optimization problems and they're easier to solve. Okay, so those are 2 classes of bound tightening. So to wrap it all up, we discussed ways of starting with non-convex nonlinear functions and constructing these enclosing or outer approximation polyhedral sets or nonlinear sets. And we initially started doing this for just simple functions, just a couple of functions that we knew how to do it for. And then I introduced a generic way of generating these outer approximation using factorable programming, factorable functions. So that now allows us to take a computational graph and then replace each of these non-convex nonlinear expressions by new variables, creating smaller outer approximation sets or over just a smaller number of variables. And I can do this in a very generic way that's very general. And then I build a branch and bound routine around that, but we realize, or you agree hopefully, that having tight bounds is very important. And so this bound tightening will actually happen each time you refine the relaxation. So each time you, for example, on my next iteration, I might add a new cut here, and now I have a feasible set that's slightly smaller, so I want to run my bound tightening again, because that then reduces it. So there's a sort of, I will continually run this bound tightening, and the bound tightening helps me to get tighter relaxations, but the branching also helps me to tighten the relaxations, which then helps me get tighter bounds. So these 2 things are sort of done continually throughout the branch and bound tree search. So those codes are quite complex, but if you want to beat them, the way to beat them is to pick a function that you know well, that's slightly more complicated than what these guys do, implement that, and you're up and running. So that's one way of beating it. Or do it for a class of new functions that maybe have a cool application. Okay, so that was a lot on mixed integer nonlinear optimization with non-convex functions. So we'll take a wee break now, and we'll come back in a moment with more news on how to detect convexity.